This reservoir appears completely still, yet the water stored behind this dam contains enough energy to rotate enormous machinery and produce electricity. The process is a chain of conversions. Stored water begins moving, drives a turbine, rotates a generator, and produces electricity for the grid.
The energy available depends on two major factors: how much water is moving and the vertical distance it falls, known as hydraulic head.
The intake admits water, while a heavy steel rack blocks large debris that could damage or obstruct the turbine's internal passages. When generation is requested, hydraulic actuators raise the intake gate. Water begins entering the pressure conduit in a carefully controlled flow. Gravity drives the water through the penstock. The elevation difference creates pressure, while the conduit delivers the flow toward the turbine. When flow changes rapidly, pressure waves can travel through the conduit. The surge chamber gives the moving water additional space and reduces extreme pressure changes. The spiral casing distributes pressurized water around the complete turbine circumference, helping deliver a balanced flow toward the runner. Adjustable Wicket gates regulate how much water enters the turbine and direct the flow at the angle required by the rotating runner. The Francis turbine remains submerged. Pressurized water passes through its curved blades, changes direction, and applies torque to the runner. The turbine does not create energy. It converts part of the moving water's hydraulic energy into mechanical rotation. The vertical shaft carries turbine torque into the generator. Guide bearings control alignment, while the thrust bearing supports the heavy rotating assembly. Above the turbine is a synchronous generator. The shaft rotates its magnetic rotor inside a stationary ring of copper windings. The excitation system supplies controlled current to the rotor windings. This creates alternating magnetic poles that rotate with the shaft. As the rotating magnetic field passes the stationary copper windings, electromagnetic induction produces three-phase alternating electrical power. An automatic voltage regulator adjusts rotor excitation. Changing magnetic field strength helps maintain the generator's electrical voltage. Electrical resistance, magnetic losses, bearings, and airflow friction produce heat. Internal ventilation and water-cooled heat exchangers remove it. Before connection, protection systems confirm that generator voltage, frequency, and phase match the electrical network. The main breaker then closes. The transformer raises the voltage so electrical power can travel efficiently across long-distance transmission lines. From the switchyard, high-voltage electricity enters the interconnected grid and travels towards substations, industries, businesses, and homes. When electrical demand changes, the governor adjusts Wicket gate opening. More water flow produces more turbine torque and greater generator output. If sensors detect a dangerous condition, protective systems disconnect the generator and reduce water flow, bringing the unit to a controlled stop. After passing through the turbine, the water is downstream. Without consuming the water, although dams can significantly alter rivers and habitats. Pumped storage hydropower works like a giant battery. Electricity moves water uphill when demand is low, and the stored water generates power when demand rises. Stored water begins moving, the turbine creates rotation, the generator produces electricity, and the transformer sends that power into the grid. Subscribe to VisiCore Science.